Hello, welcome to CS4510 L16B. This is Ladner's theorem. Ladner. He proved this theorem and then went immediately to work in some other field. I think it was like eye tracking robotics or something. So interesting history there. Ladner's theorem is Ladner's theorem basically is a question about NP. So, and again, we're in NP. There are two possibilities, right? If P does not equal NP, it could be the case that NP looks like this, where everything in NP is NP complete if it's not NP, right? Or it could look like this, where NP complete are hard problems in NP, but there's this like gray middle-ish zone that we don't really, things that might be in NP but not NP complete and are also not NP. Poll for the audience, which one do you think is the correct view of NP?
So the one on the right.
This one. But you?
I don't know what's in the middle. I don't have a example, so I don't know. Maybe left.
Okay. This tie. I'll tell you the answer is actually this one, kind of.
No.
It's not constructive though. So here's Ladner's theorem. If P does not equal NP, and it's conditioned on this, okay, then there exists an L such that L is in NP, L is not in P, and L is not NP hard. So that means there is something that goes here if P does not equal NP. Now if P equals NP, then of course everything that's NP complete is also in P. So if P equals NP, these smush together. There is, basically what Ladner's theorem proves is there is a middle-ish zone if P does not equal NP. Now the problem is, it does not do so constructively. We don't actually have any, we have 10,000 problems that go here if P does not equal NP. We don't have a single problem that can go here if P does not equal NP. We have candidate problems, but we don't know any of them. So I can tell you two example problems that we have very strong belief that go here. Recall the, what was it? The subgraph isomorphism problem, right? The subgraph isomorphism problem was, does G contain a subgraph which is isomorphic to it, right? So G comma H, which is such that G has H as a subgraph. For example, this contains a subgraph, that, right? In the sense that there is an assignment to the variable, you can sort of, and a graph is not its drawing. A graph is the association of vertices, but you can manipulate one onto the other, right? That's the definition of a subgraph. So a subgraph isomorphism is NP complete, right? Why? What was it the problem we reduced from? Does anyone remember? This is a tough thing because I'm asking you to recall something from 3510.
I want to say clique.
It was exactly clique, because a clique is a complete subgraph. So in fact, the reduction immediately went from clique to subgraph isomorphism. So subgraph isomorphism is NP complete. Now, why am I bringing up subgraph isomorphism? What about a very similar problem? Graph isomorphism. Graph isomorphism, GI, is the problem, G comma H. Not that H is a subgraph of G, but H is just straight up isomorphic to G. In the sense that they are identical graphs that are perhaps different drawings, right? Such a problem is an NP for the same reason that subgraph isomorphism is an NP, but we have very strong evidence, but no proof, subgraph isomorphism is probably NP intermediate. It probably goes here. How strange. It's almost the same thing as graph isomorphism, almost the same thing as subgraph isomorphism. Here's two pieces of evidence that we have. First off, there's a theorem from the 90s that says if graph isomorphism is NP hard, horrible things happen. I'll tell you what those horrible things are later. We need to know definitions of other complexity classes. But basically, it's the equivalent of someone saying P equals NP, right? So there's some other problem out there that we have very strong evidence should be true, but if graph isomorphism is NP hard, then that thing is false. But because we think that thing is true, then we think graph isomorphism is not NP hard. This is the theorem from the 90s, and this theorem is actually quite difficult. It goes through a long tour through many tools in complexity theory. But if it's NP hard, bad things happen. So we don't think bad things should happen, so it's probably not NP hard, okay? I don't have more intuition on that front than that. The second reason is we actually have, as of 2015, a not polynomial, but a quasi-polynomial time algorithm for graph isomorphism. Every NP-complete problem, the best algorithm we have is exponential time. We don't have anything better than exponential time for any NP-complete problem. In fact, it is known, for example, if an algorithm solves SAT in 2 to the Cn time, then C must be greater than or equal to 1. That's a conjecture we'll talk about later. But it's basically like, not only can we don't have exponential time, the best algorithms for NP-complete problems are exponential time, they are strongly exponential time in some sense. Graph isomorphism as of 2015 has a quasi-polynomial time algorithm, in the sense that the time of this graph isomorphism can be done in something that's, it's not exactly correct analysis, but it's like 2 to the O of log cubed. Something like that, okay? Now that is called quasi-polynomial time. You can prove it's a 2050 level exercise, so I won't spend too much time on it, but this is strictly less than 2 to the O of n. And it's also strictly greater than any polynomial. So you have a runtime that's not polynomial and is also not NP-complete. It's strictly, it violates other assumptions that we have. So it's not exponential time, it's something slightly faster. It's also not polynomial. And for reasons that may seem more obvious, we should not expect this to be polynomial time. It's not, I mean, it's like, the same reason we don't think SAT is, it's like, there's a lot of searching to do, you know? Laszlo Babai had this paper in 2015 where he announced a quasi-polynomial time algorithm for graph isomorphism. It was like 170 pages or something, okay? It's a lot of math, not very much algorithms. It's very, very math heavy, combinatorics heavy. And there's a bug in the paper, it's retracted, something like this. A year goes by, 6 months, I don't remember. And then he fixes the bug. Big announcement, everyone has a big party. I think he announced it actually at Georgia Tech, but. Famous story. So graph isomorphism, very strange problem. Another problem that we have as a candidate to be, oh, by the way, the name of this class, NP intermediate. I should have started with that. This is called NP intermediate. It only exists if P does not equal NP, by the way, because if P equals NP, this thing is just NP and it vanishes. But another problem we have is a very core problem for factoring, which is important for complexity theory. Let's say you have some n and k, and there exists some factor f such that this is greater than or equal to 2, and f divides n. So n has a factor less than k, right? Factoring is in NP. You can prove it's in NP just by giving a factor of it, right? That's the verifier. But the best algorithm we have for it, I think, is polar grow, which runs in time square root of the size of the smallest factor, which is approximately sub-exponential, right? It's quasi-polynomial. Question?
Probabilistic. Very
no, the deterministic algorithm, right? So there are other, this is a good point to note, is that some people may oppose the question about P versus NP as an efficiency problem because BPP is another class, we won't talk about it at all, but it's like randomized approximation style algorithms. And factoring also is not in BPP as well, not thought to be in BPP as well, but it is definitely in NP, and it's probably not in P unless we don't have cryptography, right? So this is kind of what the space is. There's 60,000 problems here, probably here. There's at most 2 or 3 problems here. There are actually maybe 10. I just don't know the others. They're like equilibrium of a Nash game. I don't know. Some stupid stuff goes here. But Ladner's theorem constructs a language that goes in NP intermediate. And he does so, and it's a terrible and useless and kind of silly language. So actually there's 2 proofs of Ladner's theorem. The first proof done by Ladner was very creative. It was a double diagonalization, where he places a problem, assume P does not equal NP, create a problem here that on the even inputs makes every polynomial time algorithm wrong, and then on the odd inputs makes every polynomial time reduction wrong. So it's a double diagonalization against all of those things. It's a bit oversimplifying it, and somehow the problem is still in NP. So by making sure every algorithm does not decide the language and every reduction doesn't work to it, by doing so, he can create a problem that exists in this class. That's the original proof. Kind of complicated, we don't care enough. And then there's a shorter proof from the 90s by Impliakidzo, which is very aesthetically pleasing, and I like it a lot, which is why we're covering it. It's probably one of my favorite theorems of all time. So, before we get into the proof, let's first, we'll do a simpler version of the proof, right? Let's talk about something called the exponential time hypothesis. Exponential time hypothesis says SAT cannot be decided in time 2 to the little o of n. Okay? What is the relationship between f and p versus np? Yes.
The time bound is larger.
I guess what I'm saying is, in a logical sense, let's suppose f is true. What must be true about p versus np?
They're equal.
They're not equal, in fact. So f, in fact, will imply p does not equal np. Okay? Why? If SAT cannot be solved in sub-exponential time, then it certainly can't be solved in polynomial time. So there's this, and we know SAT is still in NP. So we have a problem in NP, not NP. P does not equal NP. Is this a biconditional? Is this an if and only if?
No.
Correct. And this is the reason we like F. F is a stronger assumption. P versus NP is a difficult assumption to work with, right? Recall Ladner's theorem is if P does not equal NP, then these three things are true about language. But working with P does not equal NP is difficult because it could be the case that SAT could have a quasi-polynomial time algorithm and not necessarily an exponential one. So it's not necessarily true this is an if and only if. It could be the case that every NP complete problem has a quasi-polynomial runtime that is slow but still not polynomial, right? So when people say P does not equal NP, it's not precise necessarily. There's a paper, well, this is not exactly the thing, but there's this thing called Impliakidzo's 5 worlds, where he talks about 5 possible scenarios that P versus NP could be true or false, right? And it's not just like it's true or it's false. It could be the case that it's like practically true, it's provably true, but maybe not practically useful or something like this, right? It could be the case that NP complete problems are hard to solve, but practically easy, something like this. So there's a lot of special kind of fine-grained things you can get into in some of this work. So instead of assuming P does not equal NP, we're going to assume F. By making a stronger assumption, we have actually a weaker result, but it'll make the proof more aesthetically pleasing. So I'm going to go with that. The second thing I want to comment on, what is this 2 to the little o nonsense? Why would we say that instead of little o of 2 to the n? Right? This is actually a stronger notion, right? For example, 4 to the n is 2 to the 2n, which is 2 to the o of n, right? But 4 to the n is not little o of this, but it is, this is bigger than this one, essentially, right? It's for any base, in some sense. So what we'll prove is the following. Assume the exponential time hypothesis. That implies that there exists an L such that L is in NP, L is not in P, and L is not NP hard. Okay. So the way we're going to construct L is really silly. It is cheating. It's fully cheating, and it has no practical application to the theory of algorithms. Why? If this proof could be made too good, if we could actually prove something useful to be NP intermediate, that perhaps could be, we could perhaps figure out a way to remove this assumption, and that would give us some way to show, if, for example, we could just prove this without the premise, that would just prove P does not equal NP. And we know no one has proven that yet, so we probably can't do it without the premise. So the premise here will be very important. Why do I mention it's cheating? The language we're going to do is basically, you measure an algorithm as a function, not of just a random n, but of the size of the input. So what's bigger, 1,000 meters or a kilometer?
The same.
Yeah. Okay, what about 1,001 meters or a kilometer?
1,001 meters.
Yeah, sorry, let me go the other way. What's bigger, 999 meters or kilometer?
Kilometer.
Yeah, a kilometer, but there's only 1 kilometer. But you have 999 meters. That's more meters than kilometers. So isn't 999 bigger? Not really. That's kind of the cheating what we're gonna do, okay? 999 is bigger than 1, so obviously it's like, that's kind of what the cheating is, okay? Consider SAT, okay? Suppose we modify SAT to be the following. Takes a formula phi, okay? But instead of just the formula phi, pad onto the formula garbage. Let's suppose we pad 1 to the n cubed, okay? Where n here is the size of the formula. We've taken a normal SAT, and now we've just taken every single formula and added a bunch of 1s to it. For example, this would be like, I don't know, x or y, something like that, okay? Why do we do that? So we can cheat. If you were to, what is the fastest algorithm that does this? You don't measure the size of the input now as, and I'll replace n here, let's get rid of n. Let's just call this size of phi cubed. Let the input always be known as n. N here is now approximately k plus k cubed, okay? So when you measure an algorithm in terms of k, it takes how long to brute force the formula? To brute force the formula, it takes like 2 to the k time, right? So measuring that as a function of the input now is a little different. I claim this language is NP hard. Why? Give me a reduction from SAT to this language.
Wouldn't you just drop the extra ones?
Other way around.
Oh.
We want to go from SAT, we want to prove this language is harder than SAT. So give me a reduction from SAT to this something else, we'll call it that.
When you add the ones on.
Yeah, you can add because there's a polynomial amount of 1s, you add the 1s on, guess what? That can be done in polynomial time, right? It's a polynomial amount of 1s. So this is NP hard, and it's in NP for similar reasons. So it's NP complete, in fact, right? Now, suppose I did a different one. Suppose I did an exponential amount of padding. This would be like x or y. Okay, something like this. So padding a polynomial amount did not make the problem easier. I claim I pad by an exponential amount. The size of the input here is k, let's say, plus 2 to the k, okay? Because there's 2 to the k once. So n is equal to k plus 2 to the k, right? Brute force takes how long?
N to the k? Or n to the 2k?
It's 2 to the k,
Oh, sorry.
right? Let's suppose that the formula has k variables. This is this size, this is that size, right? So it takes 2 to the k time. What is that as a function of n, though?
Function of just n?
Just n, yeah. Two to the k is actually less than n, right? So as a function of the input size, this language can be decided in polynomial time. In fact, linear time. So what I'm saying here is Y have two algorithms. One brute force searches for phi, the other tries to read the input. One of them will brute force search the formula before the other finishes reading the input. Therefore, this language can be decided in polynomial time. Now, it's important to note that the actual difficulty does not change about SAT. This actually says nothing about SAT. Does not imply SAT is in P or anything like that. We are simply changing the ruler that we're using because you measure algorithms as a function of the input. Linear time means approximately, the time it takes is approximately the size of the input, up to constants and so on, right? So, deciding this language takes approximately the size of the input because we made the input so big. So, if you make the padding kind of small, it's not any harder. If you make the padding kind of big, it actually makes the problem much easier. So we've just changed the perspective, and this is in P. Do we agree? Questions on that? It is not practical. This has nothing to do with algorithms. This is simply like a cheat. We're cheating. Do you agree that cheating? But do you agree that that algorithm takes linear time in the size of the input? Okay.
That's huge.
Exactly. Unnecessarily so. Okay? So here's what L is going to be. L is going to be a Goldilocks padding. We don't want it to be in NP hard or in P. We want it to be in between. So we'll choose a quasi-polynomial padding, 2 to the square root of the size of phi. That's strictly less than exponential, but more than a polynomial. We can prove, assuming the exponential time hypothesis, that that language is the required one. We need to prove these 3 facts. It's in NP, it's not NP, and it's not NP hard. If, assuming F, we can prove those 3 things, then we have proven that it is NP intermediate exists, assuming F, right? Now I'll tell you, if you replace F with P does not equal NP, you get a very similar proof. It's just it's more complicated. Just like all kinds of little details. So I like this one because, again, for the aesthetics. Questions on that? So let's prove it. Why is L in NP? First, let's prove L is in NP. To prove a language is NP, all we need to do is give a verifier for it, right? So what's my verifier going to do here?
Evaluate the SAT and just ignore the ones.
Yeah, basically. So the verifier is going to take as input phi 1 to the 2 to the square root of phi and a witness x, and it's going to plug and chug x into phi. It's also going to do one more thing. Just count the padding. Check that the syntax is correct. For example, if the padding is too small or too big, you want to reject, right? This takes polynomial in K. This takes approximately 2 to the square root of K time, right? So whatever this is going to be polynomial time. Don't really know what it is, but it's definitely that big. Do we agree that the language is at least verifiable efficiently? The verifier has to read the whole input, but it can do so by looping over that, keeping a little math counter, right? That shouldn't take too long. And it computes 2 to the square root, and then it writes that down, and then it just checks the padding is that length. That can be done pretty efficiently, right? Okay? Now, next let's prove that L is not in P. Assume to the contrary, that L is in P. We will solve SAT too fast, violating F. Suppose the algorithm for L is A. consider this A prime on input phi. All it's going to do is write down the padding and run A, right? Y is equal to 1 to the 2 to the square root of the size of phi. Return A on input phi, comma y. Do we agree, first off, that A prime is correct? Does A prime decide SAT? Why? Because A decides L. And it is the case that this is in L if and only if phi is satisfiable among another condition. So phi must be satisfiable if A returns it. All A prime does is fix the padding in such a way that it can call A. Okay? What is the time that A takes?
Polynomial time, or, yeah.
Well, not quite. Let's figure it out. The input here is, let's say, n. Let's say phi is of size n, because there's no padding here, okay? This takes how long? This takes 2 to the square root of n time. Then this takes some polynomial in that. We don't know what that is. But it's a polynomial in n plus 2 to the square root of n, right? Whatever that happens to be, we don't actually, let's not think too hard about it. I claim that that is 2 to the little o of n. Do we agree with that? Little o, especially here. There's some square root k, something over here, but it's fine, okay? But A decides SAT in 2 to the little of n time. It solves SAT faster than exponential time, violating the exponential time hypothesis, right? High level idea again, if A solves this language, if this language was in P, then you could solve SAT in quasi-polynomial time by simply writing down the padding and asking the P algorithm, right? That would decide SAT faster than exponential time, violating our assumption that SAT requires exponential time, right? Any questions on the time analysis there? Okay. And we have one last thing to show. We need to show that L is not NP hard, right? So, what do we know? Let's assume it is NP hard, and let's try to find a problem. Assume, to the contrary, L is NP hard. If L is NP hard, what do we know about it?
It's reducible to other NP hard problems.
Correct. Actually, from a specific NP problem, which is what?
3 SAT.
Yeah. Actually, let's just do SAT, because I'm lazy. Then there exists a reduction from SAT to L, such that, let's call it psi is in SAT if and only if phi comma 1 to the 2 to the square root of the size of phi is in L. Okay. Why psi? Why phi? We don't know that the reduction maps, and this is some f of psi. We don't know that the reduction maps the same CNF to the same padded CNF. We just know it maps a CNF to a different, perhaps, padded CNF. So let the input CNF be psi and the output CNF be phi, okay? What do we know about f? We know f runs in polynomial time. Since f runs in poly time, it can only write down something of polynomial size. So let's find a relationship between a psi in the input of the reduction and a phi of the output of the reduction, right? We know that if the reduction takes polynomial time, then whatever is written down must be less than or equal to the size of the input to the k. It's polynomial, right? Questions on this step. I'm saying what the algorithm outputs is less than some polynomial than its input. Okay. What is this though? This is simply whatever the output phi is, 2 to the square root of the size of phi. We will find a relationship between phi and psi in terms of their size, okay? This is just the size of phi plus 2 to the square root of the size of phi, right? Let's just underestimate the left side. Let's just solve for phi here. What is that? That's going to be square root of the size of phi log 2 is less than or equal to k log size of psi. Questions on that? Okay, we have then the square root of phi is less than or equal to k over log 2 log of psi. This is just some constant. Let's square both sides. We get the size of phi is less than or equal to some constant times log psi squared. What does this tell us? Phi is much, much smaller than psi, right? If you think about it, a polynomial time reduction has to take some formula and map it to a padded formula. But if the formula is of quasi-polynomial padding, it had to, but a machine can write down such a big thing in polynomial time, it must be the case that this phi must be like inverse quasi-polynomially smaller in order for that to only, that's the only way that could ever make sense. A polynomial time algorithm cannot write down something so big unless this was small. Importantly, if the size of the input here is n, the size of psi is basically O of log squared of n, right? But what that is little o of n. Phi is much, much smaller than psi. So in fact, brute forcing phi but brute force phi takes something less. So in fact, it's faster to brute force phi than it is to brute force psi. But phi is satisfiable only when psi was, by the reduction. So here's the algorithm. Consider this algorithm A on input phi, okay? What we're gonna do is compute phi comma 1 to the 2 to the square root of the size of phi from the reduction. We're going to trash the padding, brute force phi. Okay? I claim that this algorithm solves SAT. Further, I'll claim this algorithm will solve SAT too fast. If psi, the input, is approximately size n, this reduction should take approximately O of n to the k, for some k. Computing the reduction takes polynomial time. How long does it take to trash the padding? Let's not even think about it, but definitely not size of the padding. Even if it is size of the padding, it doesn't really matter, right? Turing machine can just ignore it. You free it and then you don't rewrite it, whatever, who cares? How long does it take to brute force phi? Two to the O of log of n squared, right? So this whole algorithm runs in A solve sat, decide sat I should say, in 2 to the little o of n time. What's the problem with that?
Too fast.
Yeah, violates f. Our exponential time hypothesis. So we have now proven that this language L is in NP. We've proven that L is not NP, and we've proven that L is not NP hard. Done. This is one of my favorite proofs in complexity. It's like baby's first complexity theory proof. It's so interesting to work in this field. I don't really work in this field, I just like look at other people's work, I guess. But it like the arguments here I think have a kind of aesthetic pleasure in them because somehow we were able to show something exists, yet we have no better understanding of anything. We don't know anything else, right? We assumed to the contrary that L was in P, and we violated an assumption. And then we assumed to the contrary that L was NP hard, and we used the reduction to violate an assumption. So if L was NP hard, we can use the reduction as an algorithm. If L was in P, we can use that algorithm as another algorithm, right? So every theorem in complexity is, most of them appear not unconditional, in the sense like that we just know this for certain. Like we always know that P is a subset of NP. That's an unconditional result. A lot of results are conditional in the sense that you assume things, and then if it is the case that these are true, then you can show some interesting results. For example, this relies on the fact that the exponential time hypothesis is true. If we could just prove this without the exponential time hypothesis, we would just prove P does not equal NP. But notice the way that we have to use the assumption. Every part that's important has to hammer back on the premise, which is the exponential time hypothesis. We could not do this without the exponential time hypothesis, right? It also is kind of silly because it doesn't really I mean, again, we've shown something, but it is completely impractical for the theory of algorithms because we would never consider encoding formulas in such a malicious way, right? It is really a trick of the light in the definitions that this happens to exist. But it does. But that's the best we can hope for because no one can prove anything about P versus NP. Every theorem has a kind of flavor like this where you're not really sure. I mean, you showed something, but yet you don't know anything about the object you're still showing it about. So there's kind of a common theme there. It's a fun little proof, I think, and it's one of my favorites, I think. Yeah. Questions? NP intermediates on Ladner's theorem? You can imagine, had we not done F, we had done P versus NP, our arguments would be much more difficult. We could not be satisfied with the fact that the padding was quasi-polynomial. We would have to have the fact that the padding would be polynomial. So, or sorry, it would be difficult to argue this. You would have to make the argument would be much more complex, and you would have to pad by an amount that's not a nice number. It would be a much more difficult to describe number. Yeah. Simple proof. Questions? Yes.
So you're assuming F and then showing how making the assumptions that intermediate doesn't exist violates F.
Exactly. And that's a core thing. Everything has to hammer upon F. Because if it didn't, you could accidentally prove P does not equal NP. Imagine you didn't have the F assumption here. You were just able to unconditionally show a language. If you could just show it's in non-NP and NP, in NP but not NP, you would win the $1 million, right? So somehow, if you were asked to prove this in a conditional world, it's gotta tie itself back to this thing. Otherwise, if it was for free, then you would win the $1 million, right? Same thing for proving it's not NP hard, right? we don't, that would still prove it's in NP, but not in P, right? So, yeah, I don't know, everything is kind of like of this flavor. It's like,
Do we know that NP hard is not NP?
if P does not equal NP,
Only if P, okay.
Yes.
Yep, so
there
back
are,
again.
actually, there are problems that are NP hard, which are not in P, provably so. The halting problem is NP hard. That's very surprising, but it's definitely not in NP because it's undecidable, and NP is a subset of the decidable languages. So NP is decidable, at least through brute force, but still solvable at all. The halting problem, you can actually give a reduction from SAT to the halting problem. It's not too hard. Yeah. NP hard is definitely not fully contained in P, but if NP is or not is an open question. So, questions? All right.